My name is Carlo Perotta from Aldena, Italy, and today I will talk about antenna system for network resilience in SFN DAB network. In few words, how we can maintain redundancy, reliability, and the proper design for our network. And I think the key idea in SFN when we speak about resilience is not only related to more transmitter, more tower, more antennas, but we need to, in addition, how to merge and share the coverage, how to avoid the SFN interference, and how to keep the antennas in operation over the time. So in few words, we have to keep as much as possible all the advantage from the SFN benefit and implementation. A quick overview about my company, Aldena. At Aldena, we provide a complete RF solution across all the broadcasting services like DAB radio, FM radio, and digital television, and RF solution for mission critical application or monitoring activities. When we say RF solution, mainly we are referred to tailor-made or customized antenna system together with coaxial passive components that we can provide together with our sister company Delta Meccanica, so filters, combiner, rigid line connection, coaxial switches, for example. And our activities is always at the intersection between design, network planning, mechanical implementation, of course, and long-time operation. Long-time operation means resilience. So when we speak about resilience, we need to merge the know-how, the engineering, and the data. When we speak about antennas, data are, for example, simulation. This is the reason that in 2005, we introduced in the market a specific tool. Electromagnetic Lab is a specialized tool for antenna design, coverage interference capabilities, and near-field health safety compliance. Today is used worldwide, not only for operators, broadcasting operators, but also some authorities and regulators are using it. The main features of the tool is the antenna array reconstruction, so the antenna design, so we can select different antenna type, dipole, log periodic, panel antenna. We can rebuild mechanically the array, so we can select the proper distance between the element, and we can also simulate all the optimization that we can do with the antenna, so introducing down tilt, null filling, and so on. So it's really important, the antenna design. We will see later on why it's really important in a SFN network planning. Let me introduce a little case study, a typical case study implementation. This is an antenna system that we implemented in Czech Republic for the two main operators, Telecom and RTE. So it's an antenna system composed of 6 double dipole antenna, and is designed for 2-channel 9B and 10D. And we need to respect the maximum ERP provided by the authority, by the network planning. You see here the preview of the horizontal diagram. The blue line is exactly the target area that the customer provide to us in order to guarantee the best coverage in some specific area. But what we are looking for when we implement a new antenna system, we have to guarantee the reliability of the antenna over the time. So the performance have to be stable during all the time. We need to a predictable footprint. So we need to identify the pattern, the right pattern, and we need a reliable solution under mechanical stress and weather change, for example. This is the typical setup. This allow us to move to the first pillar of the presentation, the design. Why the design is so important in the network planning? Because it's the foundation of our network performance. So the first message is good networks needs always good planning. So we can have different coverage, local coverage, regional coverage, and nationwide coverage. But in any case, we need to guarantee the best coverage and the best quality in some specific target area. We need to minimize interference, especially the self-interference for the SFN. In some cases, we have to manage some RF exposure compliance, and for sure, we have to follow the network planning that we plan. So the license fulfilling, for example, or we need to make some coordination for the frequency planning. And last but not least, all the design is related to try to save as much as possible the transmission cost. So the ERP, the effective radiative power, is the magic number that we have to manage. You see that it's a combination between the transmitting power, insertion losses, and the antenna gain. So why we have to customize the antenna gain? Because the antenna gain is our efficiency. So we need to concentrate our energy in some specific direction to guarantee coverage or to guarantee protection in some area. And every time we need to make the best trade-off between power, insertion loss, and gain. And remember that when you set up a new antenna, you have also to select the proper additional components. For example, the right feeder cable, the right filter with low losses, the right combiner, and so on. So, of course, we every time we deal with available space, weight, wind load, but of course, the best solution is try to use as much as possible more antenna, more metal to increase gain and use less power saving energy. This is the key summary about the antenna design. Second pillar, reliability. Every time we install a new antenna, we have to look to excellent performance stability over the time. So be sure that the antenna manufacturer provide you exactly all the calculation for the safety factor for all the components, not only for the antenna, but for the feeder, for the power divider, for the brancher cable. Everything have to be set up with the right power rating. So in addition, you have to choose the right connection type related to the power. We need to use the antenna for multiple channels. So also the usable bandwidth is important when we use a new antenna for sharing the antenna between the operators. And of course, the return loss and SWR during across the band. And of course, we need mechanical and structural robustness. be sure that when you select a new tower, don't look only to the available space on the tower. Be sure that everything is calculated in the right way. Ask to the manufacturer to calculate the wind load of the new antenna. In some cases, it's also important the snow or the ice load that the antenna can influence the tower. And of course, select and design the proper brackets to avoid any vibration and so on. In addition, it's really important the environment resistance and the corrosion protection. So select the proper material, ask to the manufacturer. We can provide different antenna type with different material, so stainless steel, galvanized steel, aluminum, but you know, you can select the proper antenna material, also have a look to the tower position and so on, near the sea or some industrial area, for example, and select the right radon, for example. The surface treatment, in addition, it's also important, passivation, painting, and so on. And of course, the water sealing. So the radom construction, how is built the radom, the drain, and the gasket. And the tower have the lighting protection with the DC grounding and so on. So the first suggestion is ask to the manufacturer to provide you exactly the design of the antenna. So when we install the antenna, we have to follow the suggestion and the instruction. For example, we have to mount the antenna in the right distance. We have to connect the right jumper cable to the right antenna. This is the common problem. So in case of mismatch, we completely destroy the diagram. And of course, do periodical maintenance on the antenna system. Don't wait the alarm. Follow the trends. This is the important message. And perform regular inspection, check the connection, the components, look for some corrosion, for example, and make drive tests, because we need to confirm time by time all the electrical performance of the antenna. So the pattern, the coverage, and of course the return loss of the complete system. Another suggestion, in case of maintenance, use a temporary antenna. In some cases, just a dipole can maintain the minimum acceptable coverage. One dipole, one log periodic. We can save the long-term operation, reducing, of course, a little bit the coverage, but maintain the services. Some common problem when we install a new antenna, connection, for example. This is typical. Finally, this kind of not proper connection makes some water infiltration into power divider, into jumper cable, into the antenna, and finally everything burn. The jumper, the antennas, the power divider, or the combiner down. Everything is just a simple mismatch, a simple wrong connection can destroy everything. Or why we need to go on air very fast, so installation very fast. We don't need to buy any elbow, so we can just connect the cable in this way without fixing the main cable in the right way, so a lot of vibration, a lot of problem, just for saving 2 hours and mounting everything in the right way. This is typical. Let's move to the other pillar of the presentation, the redundancy. Here you see a a case study from Italy. It is the national operator, Railway. It's a big antenna system composed by 24 panels in mixed polarizations. So it's a very interesting antenna solution. It's not the typical vertical polarization, but it's a circular polarized antenna. How we can introduce redundancy in this kind of systems? For example, we can use the dual feed setup. This reduce the single point failure, improve the availability, for example, and it's a cost-effective redundancy versus installing a complete second similar antenna on the tower. And when we split the antenna, we can we have a degradation of the coverage, but can be acceptable in order to make maintenance, for example, during the time. Let's move to the last part of the presentation, and just speaking about the resilience in terms of related to the SFN network. First of all, remember that ABU and Word DAB provide a lot of documentation and ebook about how implemented the SFN network in DAB application. We can simulate the self-interference. This is really important because we can make adjustment over the time, reduce the self-interference, or move the interference in area without population. And you know, the magic number is 74 kilometers that we have to take care with the distance limit. Resilience in terms of network means that we have to evaluate our network in case of individual transmitter failure. And we can also calculate it. For example, we can make some simple calculation related to the population. So we can switch off each transmitter defined in our technical plan, in our network planning, have a look time by time, which is the population result, and identify the best scenario or the worst. Okay? No? It's running. Okay. So a typical example, 3 transmitter, total coverage 67% of the population. Switching off each transmitter, we can recalculate exactly the population that we can cover and identify the worst scenario. A real case study, this is the regional, is a regional SFN network in Italy. The operator is DAB Italia. It's a complete coverage for covering the Lazio region. The network is composed by 12 different towers with 12 different ERP value. And of course, all the network is optimized with the time offset for each transmitter to avoid as much as possible the self-interference. The total result for the outdoor coverage is 93% of the population covered. Excellent result. How the network is designed using different antenna type and different pattern for each tower. You see panel antenna, log periodic antenna, double dipole, or single dipole solution. to guarantee the coverage, to maintain protection versus the other region, or for example, in that case, I think for protect Corsica area in France from Lazio, if I remember well. Let's focus on the same network, but focusing on the city of Rome. So we can cover Rome using 3 different antenna systems, different ERP, the same as I showed you before. Let's try to calculate something about the resilience. And this is exactly an excellent case study, because in case of failure of one transmitter, we can maintain the same target coverage in the city of Rome. Of course, now we are speaking about outdoor coverage. Maybe different result if we look about indoor coverage, but it's, I think, a good example for have an idea about the resilience. Finally, we speak about design, redundancy, reliability, all the activity allow us to perform the network resilience. So don't think that resilience is only an extra cost, because we have to think about a strategy to maintain the continuity of our services, and of course to implement a reliable network. So some suggestion: use as much as possible all the SFM benefit. So the resilience happens when redundancy is planned. Perform a structured network design. Use the antenna design to control dominance, to overlap the coverage where it's possible. So use different pattern, tilt, different ERP value, also for saving cost, and of course, do best practice and quality installation, and plan as much as possible periodical maintenance for scheduling regular inspection. Thank you so much.